Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Wafi bin Tahir and I'm going to explain for the question 1 about the heat equation. So for this question, it says that a metal bar with zero temperature at both ends has heat equation given as shown here with two boundary 0 until 1. So this question asks to determine the function for 0 until 1 for the function a sine pi x plus b sine 3 pi x with this initial value for two initial value for the differentiation and one initial value for the function. So for the first step, we're gonna differentiate the a sine pi x plus b sine 3 pi x. So by differentiating sin pi x, we're gonna get cos pi x, a pi cos pi x plus 3 b pi cos 3 pi x. Then I'm gonna use the initial value. There are two initial value for the differentiation, which is 0 and 1. So by using simultaneous equation, we're gonna get a equal to negative 3b. So for the function initial value, which is 1 per 2, I'm gonna solve this equation by replacing the 1 per 2 at the coefficient of the sign. So we're gonna get a equal to 2 plus b, and we're gonna use the negative 3b value from the differentiation before, and we're gonna get our a is equal to 3 per 2 and b is equal to negative 1 per 2. Then we're gonna get our last equation value. Our last function value is equal to 3 per 2 sine pi x minus 1 per 2 sine 3 pi x. And then next step, we're gonna use the boundary condition for this equation, which is 0 and 1. And from the equation, you add t equal to x function and t function. You can get the two type equation, which is t prime kt equal to 0 and s double prime minus kx equal to 0. So for the case 1, we're gonna assume that k is positive and the value of k is lambda squared. So we're gonna replace the lambda squared value into the x double prime minus kx equation. So we're gonna get this type of quadratic equation. So I'm gonna solve this. By solving this quadratic equation, we will get our root is equal to plus minus lambda, which is a real and distant root. So by this root, we gonna get our general solution is like this. And by using the boundary condition, we will get our we can find a1 plus a1 and b1. So our a1 and b1 is value is equal to 0. So our x function value is equal to 0. So this function is a trivial case function. So because it is a trivial case, so this case is dismissed. So for the case 2, we're gonna assume that k is equal to 0. So we're gonna replace the k value, and we'll get our root for this quadratic equation is equal to 0, which is a real but repeated root. So we're gonna get our general solution like this. And by finding the a2 and b2 for this equation, we're gonna get our a2 value and b2 value is still is equal to 0, as our x function is also equal to 0. So this is also a trivial case, so this case is dismissed. So we're gonna need to do another case. So for the case 3, we're gonna assume that k is negative, where k value is equal to negative lambda squared. So same step like before, gonna find the root, and our root this time is a imaginary number root. So we got general solution like this, and this equation. So we're gonna solve this equation. We're gonna find the x function value by finding the a3 and b3 by doing the simultaneous equation by using the boundary condition value, and we're gonna get almost the same like before, but this time b3 we're not gonna assume it equal to 0, because we also gonna get the answer same like before, a trivial case. So b3 cannot be equal to 0, so we're gonna keep the b3. So the equation will be like b3 sine pi sine lambda equal to 0. So sine n pi is also equal to 0. So sine n lambda is equal to sine n pi. So by comparing the coefficient of the sine, we're gonna get that lambda is equal to n pi. So our x function value will be b3 sine n pi x. So when put in term of n, so x function, our x function will be Sn x equal to bn sine n pi x. So for the t value, so for the t function, we're gonna use the t prime negative kt equation by substituting the k equal to lambda squared, and we're gonna use the separable method to arrange this equation, and we're gonna integrate both sides of this equation. So we're gonna get that our t function is c1 exponent lambda to t, which is lambda is equal to n pi, and I'm gonna replace the lambda with n pi. So we're gonna get our last tt equation in tt function in n term, which is equal to cn exponent n negative n2 pi to t. So our t function, we're gonna be product with x, our x function from before. So we're gonna get bn sine n pi dot product cn exponent negative n2 pi to t. So by solving this function, we're gonna get our last function is 3 per 2 sine n pi and n pi x minus 1 per 2 sine 3 pi x. Next, we need to find the bn. So our bn value is like this. So as we know, our L, which is our boundary, is equal to 1. So we're gonna replace our boundary in this equation, and then we're gonna solve this equation by using trigo identity. Sin A sin B equal to 1 per 2 cos A negative B minus cos A plus B. So by using the trigo identity from before, we're gonna split this equation into two equations, which is the first equation. We're gonna solve it first from the limit of 0 until 2. So we're gonna get is equal to 0. So for the second equation, we will solve this equation like this. The steps like this from the limit 0 to 1. So after solving this equation, our equation is also equal to 0. As our bn is equal to 0, so we're gonna get our the summation of n bn sin n pi x will be equal to 3 per 2 sin n pi x minus 1 per 2 sin 3 pi x, which is the fx function value. So our ux 0 will be the equal to fx, which is 3 per 2 sin pi x minus 1 per 2 sin 3 pi x, and our uxt will be fx product with exponent negative n to pi to t, which is our t function value from before. So we're gonna get this type this our uxt equation like this. So then we're gonna replace the n value with 1 and 3 value, which is our value from before from the coefficient of sin pi x from before. Okay, which is and we will get our last value, last equation, last heat equation, u at t equal to 3 per 2 sin pi x exponent negative pi to t minus 1 per 2 sin 3 pi x exponent 9 pi to t. Okay, that's all for me. Thank you.
Assalamualaikum and a very good day to Dr. Raifa. My name is Muhammad Asirul Azam, and in this chapter, I am going to discuss about the application of PDE in our daily lives. As to prove the application of PDE in our daily life, we have referred a journal which has a PDE solution for the problem in the journal. The journal title is Analytical Solution to Heat Equation with Magnetic Resonance Experimental Verification for Nanoshell Enhanced Thermotherapy. It's written by Andrew Elliott and others from Department of Imaging Physics Unit 56 from University of Texas and with collaboration with MD Anderson Cancer Center. Next, we move on to the aims or the problem statement of the journal. The treatment efficacy of laser-induced thermotherapy is greatly enhanced by the presence gold-coated nanoshell within the tissue being treated. The nanoshells are turned to exhibit a surface plasmon resonance at the frequency of the incident laser light, dramatically increasing the therapeutic efficiency of the laser treatment. Accurate modeling of the resulting temperature distribution is essential for treatment planning. Analytic solutions are desirable because they give greater insight into physical meaning of the different terms that contribute to the problem. Next, I will explain on how PDE are applied in these journals. Based on the journal, the heat equation is solved by application of Green's function method, and the solution is compared to the experimental temperature data for gel phantom containing different concentration of nanoshells. Green function method is suitable to solve PDE non-homogeneous problem. The experimental temperature data was obtained by using magnetic resonance temperature imaging methods, while the gel was being heated with an 810 nanometer laser. Next, I will show to you the main equation applied in the article. So based on the article, the heat equation are solved by apply these Green's functions. And the green function equation are basically derived from this equation. As the conclusion, we have demonstrated to the effectiveness of analytical solutions to the heat equation in predicting the thermal distribution as a function of nanoshell concentration in phantoms where the number of nanoshell presence approximates to the aspects in tumor. Comparison between the thermal distribution as predicted by the Green's function method and the experimental measurements show good agreement, with the overall average RMS difference being 0.93 plus minus 0.84 coulomb. The advantage offered by analytical method is that once the boundary conditions are known and the initial solution calculated, the solution can be readily obtained by applying the desired laser power. Numerical methods, on the other hand, require complete recalculation whenever one parameter is changed. So, that's all for PDE application. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Suhaib bin Halimi. So now I will explain how to answer question 2, which is Fourier series question. So in this question, from the function given, we need to determine its partial sum of the Fourier series. Next, we need to prove that the n times sine x times first derivation of f 2n minus 1 x equal to 2 sine 2x. And then next question is we need to state whether fx equal to tangent x can be expanded as a Fourier series. If so, how? If not, why? So for question 2a, the function given is fx equal to negative 1 from negative pi until 0, and the function of 1 from 0 until pi. So from this equation, we can determine either this equation is an odd function or even function. So how we want to determine it? We will draw the graph from the function given. From this graph, we can see that the function is an odd function. Odd function says that we need to use Fourier sine series, which is a naught equal to an equal to 0. So how to answer this question? By using partial sum formula, which is fnx equal to a naught plus summation of an constant cos nt plus summation of bn sin nt. So because of the function is an odd function, we just need to determine the bn value by using formula 2 over L integration of fx sin n pi x over L dx. So the value we get for the bn is negative 2 over n pi times negative 1 power of n minus 1. From the value of bn, we just need to put into the partial sum formula fnx, and we get summation of negative 2 over n pi times negative 1 power of n plus 1 times sine n pi. Next, in order to answer the question 2b, first step we need to substitute 2n minus 1 from the n value in this function. Then we need to calculate for certain value of n, which is n equal to 1, and we get 4 over pi sine x, n equal to 2, and we get 4 over 3 pi sine 3x, and for n equal to 3, we get 4 over 5 pi times sine 5x. Next, we just need to rearrange the function we have calculated into the equation for f 2n minus 1x, and we get 4 over pi times sine x plus sine 3x over 3 plus sine 5x over 5 until some infinite value, which is sine 2n minus 1 x over 2n minus 1. Next, we just need to integrate the equation, then multiply by sine x, and then multiply by pi. So in this question, we use two trigo identities, which is 2 sine x cos x equal to sine 2x, and another one is 2 sine a cos a plus equal to sine a plus b plus sine a minus b. So from the equation we just need to use the trigo identity in order to solve the equation. And lastly, the equation is proved by pi sine x times first derivation of function f2n minus 1 x equal to 2 sine 2n x.
Also, for the question to see, we cannot solve this question because the function cannot be expanded as Fourier series because function is not bounded on periodic domain. So no Fourier series of tan x exists. That's all for this question.
Next, in this chapter, we will discuss about the application of Fourier series in our daily life. So, we have referred to the Journal of Application of Fourier Series in Electric Circuits and Digital Multimedia Visualization Signal Process of Communication System. Next, we will look into the problem statement background for this journal. The Fourier series, the founding principle behind the field of Fourier analysis, is an infinite expansion of functions into sine and cosines. Fourier transform provides a continuous complex frequency of a function. It is useful in the study of frequency response of a filter, solution PDE, discrete Fourier transform, and FFT in the signals analysis. The advent of Fourier transformation method has greatly extended our ability to implement Fourier method on digital multimedia visualization system. As an example, we'll show to you how to done or solve analog to digital conversion by using Fourier series. Based on the article, basically they are going to convert the analog signal system, which kind of the sinusoidal waveform, into a digital signal system such as discrete time signal system like this. So the main equation applied in this journal is the partial sum equation. So we need to compute the value of AO, AN, and BN by using this equation. Next, we will solve this equation by using partial sum method. So we need to find the value of AO, BO, and BN to use to apply the partial sum method. So we compute the value of the function into the AO equation, and we will get the answer is 0. After that, we are going to calculate a value of an by computing the function value into this equation. So it will result 0 also. As we know, when an is equal to AO is equal to 0, that means the function is an odd function. And after that, we will calculate the value of bn, and we put the value into this equation, and we'll get result like this. Next, we will put the value of AO, AN, and BN into the partial sum formula, and it will result like this. So we need to compute the H value, which is the sinusoidal or the analog waveform amplitude, into this equation, and we can plot the digital graph like this. Next, as the conclusion, the Fourier series is useful in many applications ranging from experimental instrument to rigorous mathematical analysis technique. The primary use of the Fourier transform of converting a time domain function into its frequency domain with digital communication signal. As an example, in this chapter, we have done converting the analog signal into the digital signal. So that's all for the application of Fourier series and from me. Thank you.